Today we'll discuss one of the topic, that is attenuation optical fiber communication system, and in this attenuation we'll discuss the topic absorption and the scattering losses. My name is Mr. Himanshu Nagpal, assistant professor in EC department of Akgec Ghaziabad. First of all, we'll discuss about the attenuation, and this attenuation is the transmission loss from one side to the another side. Means transmission loss when we are sending the input from when we are sending the signal from the input side and the output which is obtained at the receiver side. Clear? So the ratio between the two, that is logarithmic of input divided by output, that defines the attenuation in terms of decibel. Means if I say the output is less as compared to the input, that means I can say that is the loss in the optical transmission system, and this loss is described by the term that is a attenuation. So attenuation is one of the most important factor in bringing about the wide acceptance in the telecommunication system. So signal attenuation within the optical fiber system is as with the metallic conductor, is usually expressed in the form of logarithmic of decibel, logarithmic of input divided by output, and the unit is the decibel. Clear? So this decibel is mainly used for the comparison of two power levels which may be defined for a particular wavelength, and that is equal to the ratio of the input, that is the transmitted optical power, that is Pi, into the fiber, and the output which is received at the optical power which is received at the output, that is a P out. Means if I say this is a, let's say this is optical fiber input which is applied at the transmitter side, that is defined as that is denoted by Pi, and the output which is received at the output of the optical fiber, that is denoted by PO. It means the attenuation will be equal to what? Attenuation means loss will be equal to what? P out divided by Pi, P out minus Pi, that defines the loss, and the attenuation in terms of decibel will be equal to what? 10 log of P input divided by P output. Now similarly, if I say, as we know that this is a loss, you can see that the input power is higher as compared to the output power. If I say the output power is higher as compared to the input, that at that case attenuation is termed as a gain of the system. Clear? Now as we know that the output is always less than the input, output is always less than the input, that means I can say there is a loss factor, and that loss factor is defined as the attenuation, that is a 10 log of P input divided by P output, and the when we do the logarithmic of power multiply by 10, the output will be equal to so a number of mechanisms which is responsible for the attenuation in an optical fiber system. These mechanisms are mainly due to the material composition, preparation and the purification technique of the optical fiber system, of the optical fiber, and the waveguide structure of the optical fiber. So there are some factors which are responsible for the attenuation, that is the material composition of the optical fiber, and the technique and the preparation, the purification technique which is used in the manufacturing of the optical fiber, and the waveguide structure of the optical fiber cable. So these categories, attenuation may be categorized into the major areas which include the material absorption and material scattering, that is further divided into two types, linear and the non-linear scattering, curve and the micro bending losses, mode coupling radiation losses and the losses due to the leaky, and some losses are also at the connectors and the splices. So these are the factors which are responsible for the loss in the optical fiber system. Absorption, and this absorption is due to the material, that is a material absorption. Material scattering means the light is scattered inside the optical fiber system, so there is a loss which is related to the scattering, that is a material scattering, and this material scattering is further divided into consists of two types of scattering, it is a linear and the non-linear scattering. And if the optical fiber is bent at some point, so the losses which is due to the bending of the optical fiber system, that are known as the bending losses, and these bending losses are further divided into two types, that is the micro bending and the macro bending. Mode coupling radiation losses. Mode coupling radiation losses means if I say two or more modes are traveling in optical fiber system, then one mode of the signal power from the one mode of the optical fibers of the signal is transferred into the another mode. So that type of radiation loss is known as the mode coupling radiation loss. And some losses due to the leaky modes. These modes are generally degenerated and get outside from the core into and decays into the cladding, and that field which is decaying in the cladding, that is known as the evanescent. So attenuation is usually expressed in the terms of decibel per unit length, that is equal to alpha. Attenuation is described in terms of alpha multiplied by length is equal to 10 log of pi divided by pi, that is the total attenuation. And this alpha dB is this is the total attenuation of optical fiber system, and this is attenuation in decibel per kilometer. So alpha dB is the signal attenuation per unit length in the decibel system, which is also referred to as the fiber loss parameter, and the L is the fiber length. Means if I say this is an optical fiber system, and this optical fiber system has a length of, this optical fiber cable has a length of 10 kilometer, and the loss, let's say this is the input power which is the 10 milliwatt, and if I say output power is a 7 milliwatt. So attenuation will be equal to what? Will be equal to 10 log of P input divided by P output. And if I want to calculate the attenuation per kilometer, if I want to calculate the attenuation per kilometer, that means 10 log of P input divided by P out will be divided by the length of the fiber. One of the major factor that is involved in the attenuation, that is the material absorption, and that contributes the losses or attenuation in the silica glass fiber. So material absorption is the loss mechanism which is related to the material composition and the fabrication process, which this results in the, means due to the material composition and the fabrication for the fiber, which results in the dissipation of the sum of the transmitted optical power as heat in the waveguide. Clear? So this absorption is mainly due to the material composition and due to the fabrication technique and environment which is used during its fabrication. So absorption is further divided into two types. This absorption is further divided into two types. That is a intrinsic absorption and another one is the extrinsic absorption. Clear? Now see, first we will discuss about the intrinsic absorption. Intrinsic absorption is what? A pure silica glass is used, and due to the pure silica glass and its material structure in the near infrared region, at this point there is a absorption which is due to the pure silica glass in the infrared region that contributes into the absorption. And this is due to what? This is due to the stimulation of the electron transition from within the glass by the higher energy excitations. Means if I say this optical fiber is made up of what? Pure silica glass. Pure silica glass, when signal is transferred through optical fibers cable, the electron which is present in the structure of the pure silica glass, these electrons get excited due to the heat and electrons gets movement of the electrons gets increased, and due to this movement of the electrons get increased, there is a transition of electron transition, and that results in the loss of the signal. So the effect of both of these processes may be minimized by the suitable choice of the both core and the cladding composition. Means the absorption is mainly what? In the infrared region, in the near infrared region, and some absorption is mainly in the ultraviolet wavelength region. So in these both the processes, absorption can be minimized by suitable choice of both core and the cladding composition. For example, in some non-oxide glasses, fluorides and the chlorides, due to the composition of the fluorides and the chlorides, the infrared absorption peaks occurs at the longer wavelength, and as compared to the longer wavelength transmission with the oxide glasses. Means due to the some non-oxide entry of the non-oxide glasses, that is the fluoride and chlorides, they result in the higher attenuation in the infrared region as compared to the oxide glasses. So you will see the attenuation spectra for the intrinsic loss absorption. You will see here that in the ultrawide when the energy of electron get decreases or photon get increases, the attenuation decreases in the ultrawide absorption, and in infrared region the attenuation gets increases. So this is mainly the region where the attenuation get lower out. Next one is the extrinsic absorption. This extrinsic absorption is due to the is mainly due to the impurities which is present in the optical fiber cable. And in practical, as we know that the optical fiber cables are mainly prepared by what? Conventional melting techniques, and due to the conventional melting techniques, major source of signal absorption, signal attenuation is due to the extrinsic absorption from the metallic impurities. So some of the common metallic impurities found in glasses are given as in this. So these are the common metallic impurities which contribute to the attenuation in this peak wavelength. Means if I say that is chromium 3+, chromium 3+ is a metallic impurity which introduces the attenuation mainly at this region, that is the wavelength of the 625 nanometer. So this transition element contamination can be reduced to a acceptable level by improving the fabrication technique, or you can say by glass refining technique such as a vapor phase oxidation, which largely eliminates the effect of these metallic impurities. And another factor which contributes to the extrinsic absorption, that is a oxide or hydroxyl ions, that is a water vapor, एक तरह से means you can say molecules of the water. So hydroxyl ions dissolved in the glass contributes to the extrinsic absorption, and they act as an impurity in the fabrication of the optical fiber cable. So you will see that this is a graph which shows the absorption spectrum for the hydroxyl ion. Means you can see that at these overtones provides a higher attenuation at this wavelength due to the hydroxyl ions. You can see that around 1400 nanometer hydroxyl ions produce a higher attenuation up to the 10 to the power 3. At the around, you may observe at around 900 nanometer hydroxyl ion produces a maximum attenuation around 950, sorry. And here you can see that around 750 or 725 nanometer hydroxyl ion produces a higher attenuation at this about 10 dB per kilometer. So this is a attenuation graph, overall attenuation graph, that includes the infrared attenuation, infrared absorption, and your ultraviolet absorption. In this graph also includes the loss due to the scattering. So this is the measured absorption, this is a measured result, or you can say experiment result, and this is a theoretical result. This means you can say this is a loss absorption due to this one, that is a ultraviolet absorption. This one is the infrared, and this one is loss is due to the Rayleigh. So overall attenuation graph, which is due to the what? Absorption, scattering, polarization, loss due to the fiber connectivity, mode coupling. So overall experimental graph will be like this one. So next one is the scattering. This scattering loss in glass arise from the microscopic variations in the material density and from the composition fluctuation and from structure inhomogeneity or defect present in the fiber during the manufacturing of its fiber. You will see that if I say this is an optical fiber cable, so due to its material composition, some small size impurities or large size impurities present in the core. Clear? So this size of impurity, this size of this one structural composition results in the which type of contributes to the scattering. Means if I say that this light strike into this area, means the photon strike into this area, the light wave get scattered around this material, and this process is the scattering. And the loss, which is, means if I say this is a forward signal and this will also be the forward signal, this forward signal, the energy which is in this forward direction will be less as compared to the energy which is come from this direction, and the rest of the energy get scattered in other directions. So this scattering contributes to the loss in the optical fiber cable. So this scattering is further divided into two types. One is the linear scattering and another one is the non-linear scattering. So linear scattering is further divided into two types: Rayleigh scattering and the Mie scattering. And the non-linear scattering is further divided into two types, that is a Raman scattering and the stimulated Brillouin scattering. So first, linear scattering is what? Linear scattering transfer causes the transfer of some or all of the optical power contained within one propagating mode to be transferred linearly into the another mode. Means if I say one mode transfer its power to the another mode linearly. Means if I say the power, some power or all power of one mode is transferred to the another mode, and when there is a transfer of one mode to the another mode and that is transferred, that is a linearly transferred, and that type of scattering is known as the linear scattering. So this process result in the transfer of energy from one mode to the another mode. It means that this transfer may be to a leaky mode or a radiation mode which does not continue to propagate within a fiber core but is radiated from the fiber. Means this mode transfer its energy to some leaky modes or leaky ray. When it transfers its energy to the leaky modes or leaky ray, and this leaky ray is always decay its energy in the cladding exponentially. So main power is get dissipated, transferred to the leaky mode which does not propagate inside the optical fiber cable throughout the length of the fiber cable. Clear? So there is a loss, and this loss is known as the linear scattering loss. But if I say in linear scattering modes, after transferring its power, one mode transfer its power to the second mode or another mode, there will be a no change in frequency after scattering. Clear? So linear scattering modes, in the linear process there is no change of frequency on the scattering, and this further categorized into two types, that is the Rayleigh scattering and the Mie scattering. And these both, Rayleigh scattering and the Mie scattering, these are both mainly results from the physical problem manufactured fiber cable which are difficult to erase but it can be minimized. Clear? So Rayleigh scattering is the dominant intrinsic loss mechanism in the low absorption medium between the ultraviolet and the infrared region. Rayleigh scattering is mainly occurred when due to the inhomogeneity, when the size of this inhomogeneity is comparable to the wavelength of the light. Means the impurity which is present, when its size is comparable to the wavelength of light, and that type of scattering is known as the Rayleigh scattering. Okay? And these inhomogeneities, when I say this is an inhomogeneity, which is present inside the optical fiber cable. This mainly contributes what? Contributes to the change in the refractive index of the fiber cable, that means the refractive index fluctuations, and this inhomogeneity contributes to the change in the refractive index fluctuation, and refractive index fluctuation is, it means that there is a fluctuation in the density and the compositional variation, and these are mainly occur due to what? During the manufacturing of the fiber cable. Okay, so this compositional variation may be reduced by improving the by improving the technique of fiber manufacturing, but it cannot be avoided, but it can be reduced by improving the, by using the improved technique for manufacturing of the fiber cable. So this I have already told you. So this is a coefficient, that is the gamma r, which defines the, which signifies or defines the how much power get scattered due to the Rayleigh scattering, that is gamma r will be equal to what? 8 pi cube divided by 3 lambda square. So lambda 4 n की power 8 p square beta c k into by Tf, that is Tf is the fictive temperature at which manufacture is during the manufacturing of the fiber cable. K is the K is the Boltzmann constant, beta is the thermal compressibility, P is your average photoelastic coefficient, and N is the refractive index. Okay. Now next one is the Mie scattering, and this Mie scattering is mainly due to the inhomogeneity which have a size comparable to the guided wavelength. In that case, in the Rayleigh scattering, not comparable, size is very small comparable to the this one, and Mie scattering, the size is comparable to the wavelength of the fiber. So this results from the non-perfect cylindrical structure of the optical fiber fiber cable, that is a waveguide, which is caused by the fiber imperfection such as the irregularity in the core cladding interface, core cladding refractive index differences along the fiber cable, diameter fluctuations, and the strain is the, when this impurity size is greater than the lambda by 10, then it contributes to the Mie scattering, and this Mie scattering is mainly in the forward direction. It can be reduced by removing the imperfections of the glass at the time of manufacturing technique, increasing the relative refractive index of the core cladding, and the carefully controlled extrusion and the coating of the fiber cable, means to avoid the stress given to the fiber cable. Today we have discussed about the absorption and the scattering losses which contributes to the attenuation in the optical fiber cable. The book which I have prepared for preparing this slide, that is a John M. Senior Optical Fiber Communication Principle and Practice by John M. Senior. Thank you.